Today we're going to be looking at kinematics again. Velocity and acceleration. You already learned that if you have a displacement formula and you find its derivative, you get a velocity formula. If you find the derivative of velocity, you get an acceleration formula. So velocity is just displacement, the derivative of displacement. Acceleration is just the derivative of velocity or the second derivative of your displacement. And going this direction is our derivative. We're going to find going backwards later is our integral. Now there's a difference between distance and displacement. Distance is how far an object has traveled. It has no direction, so it can't be negative. Displacement is the net change of position. All right, so they got the example here. If you traveled the circumference of the world and then came back home, you would have traveled a great distance, but your displacement would be 0 because you're right back to where you started from. Which I think I've explained why I am not very motivated to run. Because if I go out for a run, I know it's good exercise, but at the end I'm going to end exactly where I started with and have it, taken half an hour. I could be exactly where I started with. I could watch a Netflix show also and be exactly where I started with after that amount of time. So it's hard to motivate myself to go for a run for that reason. Now, if my car is broken down and I need to get from point A to point B in a hurry, then I can run. Then I'm pretty motivated. Velocity is the rate of change of displacement. It also has a direction. So when your velocity is greater than 0, the object is moving in a positive direction. And depending on what you're talking about, we usually think of this as either going to the right or going up. And when velocity is negative, we think of going to the left or down. So there's a difference between speed and velocity. Velocity has a direction. Speed doesn't matter which direction you're going, it's just how fast you're going. And then, of course, you can find an average velocity. How far did you travel over how much time? That would be your average velocity. So there's your difference between velocity and speed. If your acceleration is positive, your velocity is increasing. This kind of makes sense. When you're decelerating, you're slowing down. Okay? But we had this already with, we talked about when you have a derivative being positive, your original function is increasing. When your derivative is negative, your original function is decreasing. And you can really see this with acceleration because it's something you experienced, right? If you're speeding up you know that your velocity is increasing. It's very hard to speed up and watch your speedometer go down. That would be very counterintuitive. So it's nice that you have seen these things already in real life examples, and they just reiterate the properties of derivatives. Now, this is where directions can sometimes throw you off, because your real life experience is only with positive velocities and positive accelerations. It's not like if you're driving if you're driving away from Winnipeg, your speedometer shows positive things, and then you start driving back, it shows negative acceleration. That would be a very confusing speedometer if they had velocity on there, and they decided on a certain direction being positive and a certain direction being negative. That could be very confusing on a speedometer, right? Oh, speed limit's at 100. I was only going negative 120 to my velocity. I should be fine. I was way under. So here's the key thing, okay? Something is speeding up when velocity and acceleration are either both positive or both negative. And it's the negative ones that throw you off. If you have a negative velocity, it just means I'm going in this direction instead with a certain speed. And a negative acceleration would just mean I am increasing in this direction or decreasing in this direction. So if I'm decreasing in this direction, but I'm going in this direction already, I would be speeding up. So if your signs are the same, then you would be speeding up. If the signs are different, one's positive, one's negative, you will always be slowing down. So you can check it by checking, if I multiply them together, positive times a positive or a negative times a negative will always be positive. And a positive times negative would always give me a negative number. That tells me I'm slowing down. So the position of an object is modeled by this function. And sometimes they like to do position questions where they just have it, it's moving along your x-axis. You might get some of those questions coming up. Find the average velocity of the object from 2 to 5. So average velocity is change in distance over change in time. So we can plug in s of 5 and s of 2. And the change in time would be 5 minus 2. The average velocity is 16 meters per second. So again, really paying attention to words here. Here we have average velocity. The next question says find the velocity. So this, I would have to do my derivative to find my equation and then plug in 4. That's the instantaneous velocity at that moment. That would be you looking at your speedometer and seeing exactly what I'm doing at that second. Average acceleration. So again here, the math is never hard. It's just what is an average acceleration? That would be your change in velocity over your change in time. From 2 to 5, so I plug in 5 into my velocity equation and 2 into my velocity equation. Divided by 5 minus 2. Make sure I have my units there. It comes out to 11 meters per second squared. To find the actual velocity, actual acceleration, we have to take the derivative of velocity and just plug in 4. And if we apply what we just learned, at 4 seconds, is the object speeding up or is it slowing down? It is speeding up because both the acceleration and the velocity are both positive at 4. It could either be both positive or both negative to be speeding up. I guess I should say the particle. You're not part of this question. All right, here's one of the questions where they tell you there's an x coordinate moving on the x-axis, having a lot of fun. And it's modeled by that cubic equation. During the first 2 minutes, what is the displacement? Wow. Well, at 2 minutes, this is where it would be, at negative 5 centimeters. Means that it has gone 5 centimeters to the left. Finding the average velocity of the particle during the first 2 minutes. Again, average velocity. Do your change in distance over change in time. Finding the actual velocity, we do the derivative, we plug in the value. Find the actual acceleration, we do the derivative again, plug in the value. And is this one speeding up or slowing down? They're both positive. So it is speeding up. So I'd like you to try the next one on your own. I'll put up the answers in a bit. How did you do? Okay. So now we have to interpret the graph and understand what's happening. The figure shows the velocity of a particle moving on a coordinate line. When is the particle moving to the right? If it's moving to the right, the velocity would be positive. Okay? When is the velocity positive? From 0 to 1, and from about, I don't know, I have to estimate there, 4.8, 4.7. I could technically find that out exactly if I wanted to, figuring out the equation of that line and finding its x-intercept. but I'm okay with an estimate right now. When is it moving left? Well, it's moving left whenever it is negative. So that's going from 1 to 4.8. When is the particle's acceleration positive? Acceleration is the derivative of velocity. Derivative, these are straight lines, right? What are the derivatives of straight lines? They're just the slope of those lines. So that's an important kind of observation to make here. That from 0 to 2, the slope of that line is negative. From 2 to 6, the slope is positive, and from 6 to 7, it's negative. So the velocity, okay, the acceleration is your derivative, and from 2 to 6, the slope of that line is positive. But from 0 to 2 and to 6 to 7, the slope is negative. And because there's sharp points on this, your derivative is never equal to 0. There's some weird things. It's actually not defined at these points because they're sharp points and you can't find a derivative at that point. So you actually have no idea what you can say about the acceleration at 2 and no idea what you can say about the acceleration. If it was a nice smooth curve, when does the particle have the greatest speed? This is a tricky one sometimes. Because if you think of greatest, usually think about maximums on your graph, right? But a speed could also be a minimum velocity, like the minimum on this graph at a negative velocity would still have a positive speed. So I've seen questions on the exam where this goes down to -3, and lots of people get it wrong, because then the maximum would be 3. Because your speed is your absolute value of velocity. So there's 2 places that you have that. At t equals 0, it's 2, and also at t equals 2. The velocity is -2, which means the speed is +2. And then from this graph, can we determine where it is speeding up and where it is slowing down? So we need them to be either both positive or both negative. And sometimes what I've seen people do with questions like this, especially if there's a graph, is a chart like this. Make my chart. I'm going to put velocity on the top, acceleration on the bottom, and then, actually, I'm going to erase part of my previous answer here. And then different values. So I'm starting at 0. When do things change? Velocity changes from positive to negative at 1, right? So I'm going to put 1 on here. Acceleration changes at 2. So I'm going to put 2 on here. Next time there's a change in one of them is at 4.8. I'm going to put 4.8 on here. And 6. Something changes. And what we can do on this graph is we can look at my graph, okay? My velocity is positive from 0 to 1. From 1 to 2, it's negative. From 2 to 4.8, it's negative. From 4.8 to 6, it's positive. And 6 to, I guess I can put 7 on here, it's positive again. Can you see how I went through that chart and did different things for my velocity? Now, my slope is negative from 0 to 2, so it's going to be negative, negative, Then my slope is positive from 2 to 6, so positive, positive. And then my slope is negative from 6 to 7. Speeding up has to happen when they're the same. So by making a chart like this, it's easy to see that from 1 to 2, they're both negative, and from 4.8 to 6, they're both positive. Everywhere else, they have a different sign. And so making this chart also makes it easy for me to say, when is the particle slowing down? We also should include in here from 0 to 1. From 2 to 4.8, from 6 to 7, but also from 0 to 1. And that chart really just makes it easy to see where things are doing that. All right, one more question. Again, I'll let you try it on your own first. Let's see how you did. So pose the graph shows the velocity again of a particle moving along the x-axis from 0 to 10. Justify which way does the particle move first? To the left, because your velocity starts negative. When does the particle actually stop? It stops at t equals 3, t equals 7, and t equals 10. Because if your velocity is 0, you are not moving. When does the particle change direction? You need your velocity to change signs. So that only happens at t equals 7. So even though it stops, it doesn't decide to change directions. It still goes negative at t equals 3. When is the particle moving left? Wherever the velocity is negative. So it's going to be moving left from 0 to 3 and 3 to 7. We don't include 3 because it's actually stopped at that moment. And of course it's moving to the right from 7 to 10. I'm going to make that chart again, because I think that's going to be helpful. And we're going to start at 0. And we're going to put in everything where either the slope changes direction or the velocity changes. Okay? So I'm going to include 1, because I've got a change there. I'm going to include 3. It looks like I'm going to include 4, 5, 7. Well, there it changes. I mean, you can, if you're unsure, put it in. I don't need 8, 9, and oh my goodness, 10. There we go. Okay, so start with your velocity. Velocity, negative, 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 positive, positive, positive. Easy to plug that in, easy to figure that out. Acceleration will be the slope of velocity. So when your lines are straight, it just becomes the slope of that line because that's that derivative. So we're going to be negative here, then positive there, then negative. What happens here?
It doesn't accelerate.
It doesn't accelerate. It's flat, right? Slope of a flat line will be 0. So I'm going to just put 0 in there. From 5 to 7, it's positive. Here it's positive, positive, and negative again. So when is the particle speeding up? We need them to be the same. There we go. When the acceleration is 0 there, does that mean we're stopped? No. It just means you're on cruise control. I love cruise control. I have some sad news. My very oldest car, the cruise control is sporadically, randomly tending towards, more often than not, stopping and not working. Because to turn on the cruise control, I hit a little button. When I hit that little button, a little light goes on that says cruise. And I smile and put on my cruise control. But lately I've been hitting the button. And no light has gone on. Which made me think, maybe it's just a light bulb. But the cruise doesn't work when the light is not on. So I know it's more than just the light bulb. Inevitably, this is going to cost me a speeding ticket. Because I set my cruise control so I'm not tempted. I was born with heavy toes, which make my foot heavier, which make sometimes my speedometer go more than it should. So I use the cruise control to stop that from happening. I'm going to get a ticket. I just know it. I'm going to blame Toyota and say you should pay for this. Okay, sorry. So from 0 to 1, 3 to 4, 7 to 8, and 8 to 9. Why don't we include 8? Because at 8, the velocity was 0. Or at 8, actually it's a sharp point, the acceleration is not defined. Sorry, not that, I was thinking about 7. At 8, that sharp point means there's no derivative. And so we can't say anything about the acceleration at that moment. It's kind of weird to think about because that doesn't really happen in real life. When is it slowing down? 1 to 3, 5 to 7, and 9 to 10. Oh, I should also, oh yeah, because from 4 to 5, it's constant. This one, when does it have its greatest speed? Well, the highest it ever gets is 3, but the lowest it ever gets is -4. Its greatest speed is 4, and that happens from 4 to 5. And that's also the time that it has its constant speed.